Hi guys, welcome back to this channel. In this video, we are going to look at the topic computer architecture. Now let's look at central processing unit. So central processing unit, CPU for short, is also known as microprocessor or processor. And we say that microprocessor is the heart of every computer system. Now, what is the function of the CPU? The CPU is responsible for executing or processing all the instructions and data in a computer system. And the CPU will contain three main components, which are the control unit, the arithmetic and logic unit, the registers, and also the buses plays an important role in helping all these components to communicate. Now let's look at von Neumann architecture. Now, in the year 1940s, the guy named John von Neumann developed the concept of stored program computer. Now, what does this mean? It means that many years back, the computer relied on human operators to be fed data when it is performing a process. So von Neumann model introduced the idea of storing both programs and data in the memory, and that is what is still in use till today. So von Neumann architecture consists of the control unit, the arithmetic and logic unit, the registers, the memory, the input, and the output. So we'll look at the function of each unit in the slides. Now let's look at the component of the central processing unit. So we have ALU, arithmetic and logic unit. What does it do? The ALU performs arithmetic and logic operations. So when we say arithmetic operations such as addition, subtraction, and multiplication, which is in form of shifting, and then it also performs logical operations, which is and, or. Now, it is possible for a computer to have more than one ALU to carry out specific operations. Now, let's look at the control unit. So the control unit manages all the operations within the CPU. It manages all the operations within the CPU. So it reads the instructions from the memory and interprets them using the fetch-decode-execute cycle. Also, during the process, the control unit is responsible for sending control signals across the control bus to tell other components in the computer system what to do. It is also responsible for ensuring synchronization of data flow and program instructions throughout the computer. So basically, it coordinates every other component in the computer system. Then we have system clock. So the system clock is responsible for producing timing signals on the control bus to ensure vital synchronization takes place. Basically, it sends out timing signal and makes sure that all the parts of the computer are working together. So without the system clock, the system will just simply crash. So that is the function of the system clock. Then we have RAM. So RAM is a storage, or is also called immediate access store, IAS. So the function is to hold all the data and programs that is needed to be accessed by the CPU. Now, the CPU takes data and programs held in the backend storage in a hard disk drive or SSD. So basically, when the computer needs to perform an operation, the CPU will take the data from the SSD and place it in the RAM to be stored temporarily so that these data can be accessed much more faster when the system needs to process an instruction. So that is the function of the RAM. Now let's look at the function of the register. So the register is also a type of memory storage, and it consists of small sets of storage. So basically in the register we also have some set of storage, and the register are also used to store data temporarily during execution of a program. So in the register we have this set of storage. We have the CIR, which is called current instruction register. Now, what is the function of this register? It is to store the current instruction that is being decoded and executed. Then we have accumulator. The function is it is used when carrying out ALU calculations. So basically it stores the result of data temporarily during calculations. Then we have the MAR, which is memory address register. It stores the address of the memory location currently being read from or written to. Then we have the MDR, which is memory data or buffer register. So this register stores data that is just been read from the memory or data that is about to be written to the memory. Then we have the PC called program counter. It stores the address where the next instructions is to be read, where the next instruction to be read can be found. So these are the functions of all the registers. When we explain the fetch, decode, execute cycle, you will understand these registers more better. Now let's look at the system buses. So the system buses are used in computers as parallel transmission components. Basically, they are like highways for data inside the computer. And there are three common buses that are used in the von Neumann architecture. So we have the address bus. So the address bus is used to carry addresses throughout the computer system. So from the CPU to the input and output port. And we say that the address bus is unidirectional. Unidirectional means that bits can only travel in one direction. It can only travel in one direction, and this prevents addresses from being carried back to the CPU. So that is the function of the address bus. Then we also have the data bus, and we say that data bus is bidirectional. Bidirectional means that it allows data to be sent both direction along the bus. If we look at the data bus here, we can see that data can be carried out, can be sent, and can be received. So it can go both ways. So data can be carried from the CPU to the memory and vice versa. Also, data can be carried to and from the input and output devices. Then we have the control bus. So the control bus is also bidirectional and is used to carry signals from the control unit to all other computer components. And we can see that it is bidirectional, meaning it can go to and fro. Now let's look at fetch, decode, execute cycle. So the CPU main job is to process instructions from programs, and for it to process the instruction, it uses what we call fetch, decode, execute, store cycle. So the first stage is to fetch the data or instructions, then it's to interpret. The next stage is to interpret the instruction, then the next stage is to execute the instruction and then store the instruction. Okay, so let's look at how instruction is being processed. So we have the control unit, which is responsible for controlling all the components. Then we have the registers here. We have the RAM, where the data is being stored. So in the RAM, we have the address and the content of each address. Now, the PC holds the address of the next instruction. So let's assume that this address is 01. So the address will be stored in PC. And then the address will be copied to MAR, which is then sent to the RAM. Okay, the control unit send a signal for the data to be obtained from RAM. So basically the next instruction is fetch from memory address currently stored in MAR, and instruction is stored in MDR. So the instruction or data is sent to the MDR. So this content is now being sent to the MDR. So after it has been sent to the MDR using the data bus, then the content of the MDR are then copied to the CIR, the current instruction registered. So the content is now copied to CIR. After being copied to the CIR, so in the CIR, this is where the instruction will be decoded. Now, when is 0, the first address here, when it has been moved to MAR, PC needs to be incremented by 1, meaning that the next instruction, which is 02, is now moved to PC. So the 02 is the address of the next instruction that needs to be processed. So after the data has been copied to the CIR, then the instruction is interpreted. And after it has been interpreted, then it is executed. So that is how the fetch, decode, execute cycle works. Now let's look at factors that can determine the performance of a CPU. So while the CPU is processing instructions, the CPU can process data as quickly as possible. And there are so many factors that determine how fast the CPU can process those data. So the first one is system clock. So system clock determines how many instructions that can be processed per second, and this is measured in hertz. So the higher the clock speed or the frequency, then the more instructions the system can perform. So a typical computer would be able to perform 3.5 billion clock cycles per second. So when we increase that, then the system will be able to perform at higher speed. Now, if we increase the system clock speed, this is called overclocking. Okay, it means that we are running the CPU at a higher clock speed than the intended speed, and this can boost the performance of the system. However, this can also lead to some problems. So its execution of instructions outside the design limits can also lead to unsynchronized operations, and the computer would frequently crash and become unstable. Also, it can lead to overheating of the CPU, which will also then lead to unreliable performances. Another factor that can determine the performance of the CPU is the cores. So using different number of cores can improve the computer performance. So the idea of using more cores will alleviate the need for us to continually increase the clock speed. So more cores allows a CPU to perform multiple tasks simultaneously. However, Doubling the number of cores doesn't necessarily mean that we are doubling the performance of the system, since we need to take into account that the CPU needs to communicate with each core. And while communicating with each core, this will then reduce overall performance. So many computers have dual core, which means that the CPU is made up of 2 cores, or it can be quad core, which means that the CPU is made up of 4 cores. Now, another factor that can affect the performance of a computer is the cache. So the cache is also a memory in the computer system, but unlike RAM, the cache is located within the CPU itself, which means that it is much more faster to access data from the cache than the RAM. So the function of the cache is to store frequently used instructions and data that needs to be accessed faster, and this will improve the CPU performance. So when a CPU needs to read the memory, what it will do first is to check the cache first to see if the data is there before moving on to the RAM, if the required data is there. So the larger the cache memory size, the better the CPU performance. Next, let's look at the instruction sets. So what are instruction sets? So every CPU has what we call instruction sets, and we say that they are sets of common operations that has been developed by processor manufacturers so that the CPU can operate efficiently, so that the CPU can perform its operation efficiently. And each operation will instruct the ALU and the control unit what to do. So an operation would consist of opcode and an operand. Now, what does opcode means? So basically, the opcode will tell the CPU what operations needs to be done. Okay, what operations needs to be performed. And the operand tells it what data to use or where to find the data, or it can refer to the register in the memory. So for example, an operation is load 10. So the load is the opcode, which is it tells the CPU what to do. So what to do is to load, and the operand, the data is 10. Now let's look at embedded system. So embedded system are systems that consist of the combination of hardware and software, and it is designed to carry out a specific function. So, and we say that this hardware can either be electrical, or electromechanical. Now, embedded systems are based on these 3 items. An embedded system are based on these 3 items, meaning that an embedded system would have either of these items. Now, let's look at the microcontroller. So a microcontroller would have CPU, and also it will have RAM and ROM and other components that is embedded onto one single chip. So together, these items can carry out a specific task. Now, a microprocessor will have a CPU on the chip, but there are no RAM, ROM, or any other peripherals. So meaning that this needs to be added separately. Then we also have the system on chips. So this system on chips will contain a microcontroller as one of its components, and they almost will include the CPU, the memory unit, the input and output, and also the secondary storage on a single microchip. Now, an embedded system can either be programmable or non-programmable. What does this mean? Non-programmable device means that they are devices that needs to be replaced if they require a software upgrade. While programmable devices permit upgrading of the device. So if you are using a non-programmable, this cannot be upgraded, meaning that you will need to discard this device, while programmable can be upgraded. And there are two methods that are used to upgrade programmable devices. So for example, a fitness tracker. This can be upgraded by connecting the device to a PC or installing a new software. While for automatic updates, we can update using Wi-Fi. For example, a smart car. A smart car can be updated via Wi-Fi. So these are examples of how programmable devices are updated. So an embedded system would consist of these features. Okay, an embedded system would have the user interface. It would have a software and hardware embedded in it. It would have some form of output devices, and also it would have analog or digital input device. So here are some examples of embedded system. So we said that embedded systems are everywhere, such as smart motor vehicles, lighting systems, vending systems, washing machines, which we have in our homes, GPS systems, electronic calculator, central heating system, and so many others. Now let's look at an example of an embedded system. So we have a security system, and this security system would have input device, okay, the sensors such as temperature sensor, pressure sensor, acoustic sensor, and the microcontroller would have the storage, SSD, RAM storage. So data from the sensor is sent to the microcontroller, okay, and then the microcontroller checks this data that is stored in the SSD against the preset value. Okay, the preset value can be maybe the temperature should less than 7 degrees. Okay, so the data that is imputed from the sensor will be compared to this preset value, and based on the preset value and the instructions that is already in the SSD, an output can be signaled. So an output can be signaled. An output can be to flashlights. It can be to sound an alarm, or to send a message to the home owner via their mobile phone. Now let's look at the benefits and drawbacks of using embedded system. So we said that embedded systems are small in size, therefore it is much easy to fit into devices. Compared to other systems, they are relatively low cost to make, meaning that they are not expensive to make compared to other systems, and they also consume very little power supply. Also, they can be controlled remotely using a mobile phone. So meaning that from from your maybe from outside your home, you can control all this embedded system in your home. Then the drawbacks: it can be difficult to upgrade some devices to take advantage of the new technology. So if the device is non-programmable, meaning that it cannot be upgraded. Also, troubleshooting faults in the device becomes a specialist task, meaning that to make changes in the device, then we need to get someone who has the knowledge of the device. Also, any device that can be accessed over the internet is open to hackers, virus, and some other security risk. Lastly, due to the difficulty in upgrading and fault finding, devices are often just thrown away. For devices that cannot be upgraded, then these devices needs to be thrown away. So these are the benefits and drawbacks of embedded system. Okay, thank you guys so much for watching. Please do not forget to like, share, and subscribe.